All right, guys, so limits. Just a brief overview of what happened before. So in calculus, and that's pretty much the beginning, you can consider it our first lesson. F of c means what you do is you plug in c into the function and evaluate. That's something you learned before. Now, with limits, what do you do? Would anybody like to remind me? What do you do when I say limit as x goes to c? And be very simple about it, please.
Limits are close to any number that's close to I would say x or c. So it's like our range of decimal points, but it's close to the original number or x.
That's beautiful, James. Thank you. Right. So again, we plug in here only one number, and here we plug in a huge amount of numbers, but never C. We plug things that are imitations of C. And that's pretty much the conceptual difference. Sometimes doing one process or another results in the same solution. Oh, Brian, I did start the recording, but would you like to say something? I'm glad anything you say, I enjoy it. So, all right, good. So x goes to c, and we just plug in similar values. I think maybe in the next lecture, there were some people in the morning session that voted, the others could not care less. I hope you would be excited. I'm going to try to teach you delta epsilon. I might actually send you a prior video already of my previous lecture. Maybe you will know it better. It's actually a simple idea, but only once you actually visualize it. Before that, it might seem strange, okay? So what you do is, the analogy would be a water gun. You will see it below. All right, so here is just, that's roughly what you do. But the problem with the table is that you are not listing all possible approximates, right? But here you have, let's say you're approximating -1. You're approximating -1 from below. So you have a sequence. It's an infinite sequence of ever better approximations of -1, ever better imitations. And then you are seeing a sequence of outputs, and the outputs seem to be going to -2, okay? But the problem with the table, again, is that those are just particular points in the river. It's not showing you the flow of the entire river. Do you understand what I mean by that analogy? It's like this is the position of maybe a leaf floating on the river, and you take snapshots of it. You don't see the entire flow. Maybe some other droplets of the river move you far away. I hope you understand what I mean by the river, right? Okay, anyhow, so this we all did, I think, last time, if I'm not mistaken. Here is what you actually should visualize, okay, what I visualize. Okay, that's my example. I used to be very proud of it. So you see, I imagine a water cannon. So what you do when you plug in -1, it's like you are plugging one water particle into the gun, and it shoots off somewhere. Now, what do you do when you take a limit? You put a plug over the -1. That means you cannot shoot it. You cannot feed it into the hopper of the gun. But you open up this valve, this pipe, and everything within this pipe will be pushed into the cannon and then squirted onto the wall. And you see a stream gushing onto the wall, okay? Now, that's not the limit just yet, right? Those are just initial approximates. Then what you do, you start tightening the faucet. As you tighten the faucet, let's say eventually it becomes the size of this green opening. It becomes the size of the green opening, and the water might actually get, the water current might actually get narrower, like from a water gun, right? Might actually get narrower. And if I squeeze it to the red region, even narrower. And it basically, it looks like the entire flow is focused around one point, around 2. And that's the idea of delta epsilon. Delta epsilon will describe that procedure precisely, right? Epsilon, just a preview, will describe the size of the stain, and delta will describe the size of the opening. You see, so the delta epsilon proof is this. It tells you there is a delta. In other words, I can squeeze the pipe narrowly enough so that for that particular epsilon, for that particular tolerance of width, it's like engineering type of idea here, right? All the water particles land within that region. Do you understand roughly what I'm saying? That's in a nutshell what delta epsilon, and that's how you understand limits. So we did one-sided limits. One-sided limits, it's the same idea, but if it's let's say approaching C from below, that means that if c is equal to -1, I'm just opening half a valve up to -1, but I'm closing the right part. Okay, I'm just opening this and I'm squeezing only the left wing. Or if it's from the -1 plus, I'm squeezing the right wing and the left wing is entirely inaccessible. It's closed. Okay. And I think we did this exercise, correct, guys? F of x equal to this, it's piecewise function. I think we did it.
Yeah.
If I remember correctly. Plug in 3, plug in 3 minus, plug in 3 plus. I believe we covered that. Okay. So I think we ended up with limits from graphs. Okay. And I always, whenever I see a graph, I tend to ask this question. I'm sure I asked you the same question last time if we got to this point. This graph, guys, you see this this curve here. So this is generated, we have some function f of x, and we have the x coordinate is x, and the y coordinate is f of x. The f is creating the altitude at each point x, right? So my question is, what's the dimension of this landscape? Type your answer, please.
We already did it.
Yeah, I did it correctly. Good.
Yes, it's one single dimension.
One single dimension, and you understand roughly why. Actually, you have pretty strange questions. You might ask yourself, are we living in a one-dimensional world? Right? And you might think, obviously not. We need 3 coordinates to specify where we are located, but there is the existence of something known as space-filling curves, for example, right? So it's possible to take a curve and, let's say, and fold it around this paper so that everything is colored black. You see this curve? You can take the pencil and you can move your pen around until the entire piece of paper is colored black. You might think, well, that's obvious. There's nothing problematic about it. The problem is that this has thickness. You see, when I draw with a pen, I'm not actually drawing a one-dimensional object, right? Because the ink has thickness, right? But if you have no thickness, in other words, the thickness is 0, that's still possible to cover the entire page. Like with a wire, go over and be everywhere. And that's something that many mathematicians did not believe would exist until in the 19th century, one example was found. Once one example is found, you find many others, okay? And those are pretty interesting ideas, but later, possibly. I don't want to digress way too much. There are so many exciting things around. So did we do this limit? I think it's obvious that left or right, we're approaching, when we take limit as x goes to 5 from the right or from the left, we're approaching the altitudes too, correct? So in this case, left and right limit are the same, and therefore the limit exists. And 5 I cannot plug here because it's not defined at 5. Here is the next graph, guys. Would you please be so kind and tell me what is the value of f at -1? So that's -1. What's the value of this function at -1? In other words, I'm asking if the doll is placed over x coordinate -1, where is it going to stand relative to the y-axis? How high will it stand?
-2.
Exactly, guys. It's -2. Thank you, Malika. It's -2. And the reason for that is you have this solid dot. You see, I drew this solid dot, this nail, that's where the doll is. Okay. Next question is this. Question B and C. Would you please be so kind and answer it? Here, I'll show you the graph. You understand it's just walking to -1 from left or right. And so I hope you remember it, right? So what happens if I take limit as x goes to -1 plus? In other words, -1 plus, meaning that x is always slightly bigger than -1, slightly to the right. What's going to be the situation?
Can you repeat what
Right,
question?
limit as x goes to -1 plus and limit as x goes to -1 minus is what we're interested. Let's start with the plus. Good. Carolina, you're hiding today. No worries. Just trying to coax everyone out.
Can you scroll down a little bit?
Sure. Good.
Thank you. Yep.
Exactly, Brian. So you understand what you're doing when you're saying limit as x goes to -1 plus. Don't look at it as just a bunch of letters. You try to get at the meaning, and the meaning is that x is to the right of -1. So here's -1. -1 plus means I'm to the right, and I'm walking the x to -1. So I'm having this motion. You see that? This is just translating to motion, and then I'm tracing what's happening to the altitude. So f of x is the altitude. And the altitude looks like it's going to 1.5, correct? Now, it's a little difficult to depict it by a graph. What do you think happens if I move from the left, -1?
Is it still a range? Because it's still because since it's 1.5, right? It's still
Mhm.
it's still doing like the limits, right? So instead of 1.5, it's gonna do like, for example, 1.6, and then -1 is gonna be like 1.4. It's like a range. Is it doing that or no?
You mean is it oscillating? Is that what
Yeah.
you're asking? Yes.
Yes.
So this is something pretty interesting and something that you can never truly draw on a piece of paper, but such examples exist. You can give an illustration, right? I just haven't done so, but they do exist. So the limit does not exist because look what happens. You put a person on this. You put the person here, and you walk the person. He goes down to a valley, up, down, up, down, up, down, and there are infinitely many valleys and peaks, and it's roughly ranging from 2 to 0.5. No matter how much you zoom in, no matter how close you get to -1, sometimes you are up near 2, sometimes you are down near 0.5 or somewhere in between. And such functions exist. In fact, you can create, if you take a sine, sine, and you take a spherical mirror, it will reflect infinity into 0. And that will be, if this is where 0, that will be the situation. You can easily construct such examples, but you cannot draw them. Yes, of course. Can you explain limits, Rafid? Limits in general. It's very simple. Limit in general is, you know what it means to plug in a number into a function, correct? You do that all the time when you order soda machine. Yes, guys? Have you buy a soda machine? Do you know what soda machines are? They're functions. Their input, let's say you write the number 12 and you get a Coca-Cola can, right? So that means the number 12 was processed by the machine and transformed into a Coca-Cola can, okay? So this type of machine transforms numbers into soda cans, into something like this, yes? Now, the functions that we consider in calculus transform numbers to other numbers. That's usually what they do, okay? And what you have is you can input a huge range of numbers. So let's say when I take limit as x goes to -1, what I do, I don't plug -1, but I plug many imitations of -1. You get it, guys? So all it is, limit is the same thing as plugging in, but I don't plug -1. You see here, I don't plug -1. I plug, let's say, -0.99999, and that's not good enough. I plug something even better approximating -1, right? Either from left or from right. That's everything. That's all. That's what limits are. Just not plugging in one thing, but trying to plug in imitations of the number you would have liked to put into the function, okay? Because possibly it's dangerous to put this number into the function, or possibly there are some strange tendencies when you plug in something very similar, you understand? Like it's something very chaotic or turbulent around -1. It's like it's a river of lava, right? So you flow somewhere else, and on -1 you might have this island of safety. So Okay, so this is the called divergence by oscillation. And if you did a delta epsilon argument here, what you would see in this canon, you would see that you see the stain never, no matter how short is this delta, this left-sided delta. That's the idea. No matter how much you squeeze, you see this red cursor moving. Yes, I squeeze it, squeeze it, squeeze it, and then the current is fed into the function. No matter how much I squeeze it, the stain on the wall, the current will be spraying still between 0.5 and 2. Always, you understand? So I cannot narrow the beam no matter what I do, and that means the limit does not exist. In this case, does not exist from the left. Do you follow my explanation, guys? The delta epsilon is very simple. I'm already telling you a little bit. Delta is the control over the input, right? So when you take a limit, you are feeding always not one value, but actually infinitely many. And what you do, you feed them not just so you begin feeding from here, and then you narrow the valve. Right, so that's the analogy. Limit is doing this, narrowing the valve, so feeding always infinitely many values, but less and less and less, and you squeeze towards the desired value. So you see, everything from this wall to -1 is really a good approximation of -1, and something even closer, it's even better approximation. So delta is a measurement of how good is the approximation, how good is the fake imitation of -1. Okay, good. So the limit at -1 doesn't exist because the left-hand limit doesn't exist. So then let's consider infinite limits. Let's see if you could do that without my help first. So I have x going to 0 of 1 over x squared. The question is, find this expression if it exists. Well, Victoria, factor, thank you. You say 0 squared is 0, but we don't plug 0. Remember that. So you might be correct, but we are not plugging in 0. That's the main idea here. We are plugging something similar to 0. And if you plug something similar squared to 0, we get something small, but not 0 actually.
So can't you plug in fake 0 or like 0.001?
Yeah, you plug a fake 0, right? And once you learn to do it, you don't actually bother saying 0.0001. You actually imagine just something slightly bigger than 0. I imagine a host of values.
Wouldn't that be 0 then? Because
no,
it's so close to 0.
It would not. Because again, you have to understand that we're not plugging a number. If this is 0, what am I plugging? I'm having an interval that I'm squeezing around 0, but avoiding 0. You see, so I'm plugging this entire interval, and I make the interval smaller, and then I plug it, and I make it even smaller, and I plug it. So I always plug infinitely many values into the function. So it's like water, and I'm trying to see what happens to that water. Yes, Christian. So it will be positive infinity, and let's actually examine why. Right. So let's for this I will construct a table just to show you what happens. Right. So we have x, and 1 over x squared is our function. So it doesn't matter if I plug plus or minus 1 over 10, because when I square it, negative or positive numbers squared are positive, correct? You can, by the way, I mentioned to the other class, you should wonder about it. Why is negative times negative positive? I'm sure not many of you know the answer. or have thought about it, really. Nothing is arbitrary. If you studied something in your school and you kind of remembered it, if you don't have an explanation or somebody told you it's a rule, and then it's wrong. You see, that's not how you do mathematics. But we'll get to that later. So not to digress, right? We just for now ignore this question. So squaring this number will give us 1 over 100. Now, what is division? When you take 12 and 12 apples and divide by 6 kids, each kid gets 2 apples, correct? That's what you report. When you say 12 divided by 6 is 2, you are saying how many apples per 1 kid, correct? Okay. Brian, so hold it. I would look at what you say afterwards, right? So because I tend to be distracted myself, I really appreciate that you wrote something about negative numbers. We will discuss it slightly later. I hope you will not forget, right? For sure, it's something very interesting. So here again, right, guys, why is this 100? One simple reason here is imagine that what you have is now 1 apple is divided by 100th of a kid. It means 1 apple goes to 100th of 1 kid. So the full kid is 100 parts of 100. So the kid gets 100 apples. Do you understand why this is 100? I mean, you can kind of do algebra, but I'm saying you can see that without an algebra. What is 1? It's 1 apple per 1/100th of a kid. You understand? So if you have 1 apple per half a kid, and then it's 2 apples per 1 kid. Really. That's how you report it, right? So that's why the answer is here 100. You follow me, guys? Similarly, here I have 1 over 100. If I plug it in, I square it, it ends up being 10,000. And if I put 1,000, I get, well, I get 1,000,000, and so on. And what you can see is that as I approach 0 from either left or right, what's happening is, well, I'm getting here very large values. Now, guys, here is a question. So I get this. It's called, this sideways 8 represents, well, this idea of going to infinity. Now, my question is, does the limit exist? So limit as x goes to 0 of 1 over x squared, we get this value. So do we say the limit exists, or do we say the limit does not exist? Write your answers, please. Okay, thank you, Ikra. Thank you, Said. Thank you, Alan. Okay, any other answers? Muhammad, you're asking a good question. Okay. So here is, it depends on what you consider this thing to be. Okay, so for us, we consider the answer to exist if we get a real number. A real number means 5, 7, 8, whatnot, right? Or pi. An infinity, guys, that's, by the way, not even infinity. That's a very wrong name for it, okay? There are infinities, really, real infinities. We might actually talk about them very soon. But this is just a wrong wording. We say infinity, but really this means growth without bound. It's a dynamic idea. So what you should think is, what I think is a balloon that expands and becomes bigger and bigger and bigger, okay? Or maybe a person that becomes taller and taller and taller and taller, right? But at no moment is this person of infinite length or the entire length of the number line, okay? So this means simply growth without bound. It's a dynamic property, not a number in our context. So Carolina and whatnot. So this in our context, there is, again, I don't want to confuse you. In complex analysis, you can assign this symbol to be the North Pole of a stereographic, well, of a Riemann sphere, okay? And then it will exist in that sense. But for us, in the real number system, this is just a tendency. All it means is that we're moving on the number line up. So if it's the y-axis, we're just moving up and up and up and up without ever stopping from moving up, right? But at no moment do we actually contain infinite length. So I call it growth without bound, but simpler to pronounce infinity. But that's, remember, it's not the right description of it. So it diverges to infinity, or it diverges by growing without bound, because it does not approach a definite number. Make sense? All definite numbers on the number line are just markings on the ruler. And eventually, the symbol just means you move up and up and up and up. You move beyond any marking on this ruler. Okay, so in our context, it does not exist. And you just can describe better how it doesn't exist. Here is another question, guys. Let's see if you can do it. So limit as x goes to 3 plus of 2x over x minus 3. And the same with 3 minus. Please help me. Tell me, what is this thing? What am I getting? You see, it's a quotient. It's 2x divided by x minus 3. And here I have 3 plus, and here I have 3 minus. My question is, so if I do that, if I carry out this limit, what am I going to get? You see what this means, guys? This means I'm moving towards 3 from above. I'm bigger than 3. And this means I'm moving to 3 from below. So I'm always plugging in values that are slightly smaller than 3, but only very slight. Okay, guys, when you're ready, you let me know, okay? Or give me the answer. So Brian says 3, and the other part so is minus 3. We'll see. Well, Christian, so when you say the limit approaches 3, again, x, we have to be sure we understand what we're asking. X is becoming 3. In this case, it's becoming 3, but being slightly bigger than 3. But we're interested in this quantity. This is the function. So what happens, you put the input in here and in here. So it's 2 times the input divided by the input minus 3. And you see what's happening.
Should I explain it?
Are you ready, guys? Who wants to explain? Christian, you want to explain it?
I thought you were just asking me a question.
All right, so I don't know. I suppose go ahead. You want to explain it? Explain it.
As I input the numbers, getting closer to 3, the higher the number goes, so let's say if I put in 5 or 4, the numbers do get smaller, but if I put 3.5 or 3.1 or 3.01, it gets bigger. So it does increase to infinity, positive infinity, sorry.
Yes.
But it doesn't touch 3 on the graph. So if we were to map it out, it wouldn't touch.
Well, of course not, because when we're taking the limit, we're not plugging in 3. Plugging in 3 is not allowed since we will divide by 0. Divide by 0 is not possible, right? So what we do, we plug in values closer and closer to 3. Some of you might have constructed tables, right, Carolina? You think you can construct a table? That's fine. It's just there is a much easier way of visualizing. Okay, let me try to explain to you. Okay, what do you imagine? You don't need to imagine the exact value, just imagine what you put here is slightly bigger than 3. So if you multiply a number slightly bigger than 3, I call it a 3-like number. So put here a 3-like number, what do you get? On the top, just the top. Guys, 3-like number
Just
here.
above 6.
Sorry?
Just above 6. 6 positive.
Just above, or 6 plus, right? You get 6 plus, 6
that's
plus or 6 minus don't matter because 6 plus and 6 minus are essentially 6. 0 plus and 0 minus matters because 0 plus is positive, 0 minus is negative. That's the only reason 0 plus and 0 minus matters, right? So essentially you get a 6-like number in here. What do you get in the denominator? And that's important. You plug a 3 plus here. You see, when I say plug a 3 plus, I'm just saying I imagine plugging a sequence of numbers close to 3 but slightly bigger than 3, right? But plug a 3 plus here. What do you get here? 0 plus. Thank you, Mohammed. So what is 6 divided by 0 plus? Which means 6 divided by numbers slightly bigger than 0, maybe divided by 1 over a million. 6 divided by 1 over a million is 6 million, yes? So 6 divided by 0 plus, or any positive number divided by 0 plus, will give you what? Plus infinity. Do you see that? Plus infinity, by that I mean it just will grow without bounds. So 0 plus means I divide by smaller and smaller numbers, so that will make the expression larger and larger. Dividing by small numbers makes the entire expression very large. So this is plus infinity, whereas in the second situation, I will scroll below, I'll show you again. In the second situation, I have 6 minus here. It doesn't matter 6 minus or 6, so I can say a 6-like number in the numerator, and the denominator is a 0 minus number, which means I'm dividing 6 by negative numbers, but that are very small, so I get minus infinity. Another thing is, this is not necessary for this problem, but you could, for example, I call it wishful thinking. That's how I solved this particular one. I can, instead of dealing with 2x, I figure, say, I would have liked, say, I can factor the 2, I would have liked the numerator to be x minus 3, because then I could cross it out. Okay, so I put x minus 3, and then I pay for it by adding a 3. That's called a pattern recognition, wishful thinking. You don't like the problem that you have at hand, and you replace it by the problem you would have preferred. If you learn to do that, guys, the entire subject would look like maybe 1 or 2 problems, eventually maybe like 1 problem. So everything we learn is a repetition of the same idea many times. So, but when you modify the problem, you have to pay for it. See, so it's x minus 3 plus 3. That's where I pay for it. And so here I can cross it out. That's 1. And here I'm left with 3. So then I multiply the 2 in. So it's 2 plus 6 over x minus 3. I can simplify it this way. Okay. And then if I push x going to 3 plus, I'm not saying that for this problem it's particularly useful there. You have 2 plus 6 over 0 plus, which will be 2 plus infinity, which is infinity. Again, not infinity. This means just growth without bound. 2 plus something that becomes larger and larger and larger will just become larger and larger and larger. Okay. And if I put 3 minus, I get a 0 minus, and it will be minus infinity here. So that's what we get. Okay, let's move to the next lecture note.
I don't understand how you got
Sorry?
I don't understand how in that question you got 2 and then like x minus 3 plus 3. How'd you get that?
That's just algebra. Look at it. I factor the 2, I bring it here. Okay, I put it here, and then I see x on the numerator, but x looks like the beginning of the denominator. So I put x minus 3. The reason is that if it were x minus 3, I could have just simply crossed it out.
Oh, okay. Yeah, okay.
You understand? So it just in this case, it doesn't help much because I mean you can just directly look at it and do it directly without any problem. Okay, but you will see in later examples. So the entire thing that you have to do is if you like comics, I'm not sure if that's what you are into. It seems that they release a lot of movies about it, but it's like the Superman thing, right? Superman puts the glasses. Suddenly you don't recognize him. He removes the glasses and then, oh my God, it's Superman, right? So if you are not going to be confused by the glasses, you will see that the same problem repeats itself again and again and again. So you will see that many problems are actually the same thing. Okay?
Got it.
Okay, so let's see here. So we are now going to learn how to calculate limits using limit laws. So limit laws are just, again, to prove them. That's, you see, for calculus, I suppose delta epsilon argument is specifically designed for calculus, right? At our level, to deal with the delta, to deal with the rigorous presentation of the limit laws. Because if you prove them, a lot of the other consequences you don't need delta epsilon for. So here is what the limit laws are stating. Okay, limit as x goes to a of f of x equals to L. Suppose we know that. Somebody told us that, or somehow we know that. The limit of a function is L, which means as x becomes a, the function becomes L-like number. As x goes to a, g becomes M-like number. Then the following will be true, right? So what is f plus g going to become? This becomes like L, this becomes like M. So you might imagine the summation becomes L plus M. Good? So that seems intuitive, correct? Like intuition, I mean, it seems like it's not too dangerous. Great. Now, if I have a constant times the function, well, the function is morphing and becoming an L, so you might imagine constant times L seems very natural. And there is the product rule, right? So if f becomes L-like number and g becomes M-like number, you would imagine that the product will be L times M. You understand? So it seems very intuitive. And then law number 5, x goes to a. We have numerator becoming L, denominator becoming M. So you expect to have L over M. And that's true as long as the denominator does not become 0. If it becomes 0, you need to do extra work. Okay? So guys, let me just ask you a silly question. It just itches me, so maybe it's an interruption, but you look at those limit laws. How many of you think that those laws are self-evident? Like it's obvious based on what we understand, right? Given that f becomes L and g becomes M, the limit laws are obvious. Let me know if you think so. It's good if you think so, naturally, right? I just want to know if you do or do not think that they are obvious. Do you see the idea? Right? It seems intuitive. It's almost self-suggested, right? This f somehow we know becomes L. This g becomes M. So it seems that those laws, I mean, they're too obvious to need proof. Do you agree? Now, if you agree, let me ask you this question. Have you thought about this die thing? So you know, to get admitted into this probability club, if you're at this problem, you have to toss a fair die until the pattern 5, 6 emerges, right? So you toss it once, twice, 3, and you have to toss it at least 2 times, correct? Until you have the pattern 5, 6. And then you pay for the number of rounds that you played. That's how you do your contribution. And the other game is the same, but now you toss the die until the pattern comes out 5, 5, and then you stop for the first time. So if you're lucky, you throw it only twice, and you get 5 and 5, and that's it. The game is over. Then you just pay $2 for it. No, only one die. Very important. I throw only one die. For this problem, that's important. I throw it at a time, right? So I throw a die. Let's say the number is 4. Then I have to throw it at least 2 times more, at least, right? So I will not pay less than $3 if the first throw is a 4. Good. So I throw the die. Let's say 4. Then I throw it again, and it's 7. Then I throw it, and then it's 5, and I throw it, and it's 6. So now I pay $4. You see, because 5, 6 stops the game, I pay $4. I pay for each toss of the die. That's with the 5, 6 termination. 5, 6 is the code that terminates the game. Now, the other part of the game, you can choose to play this game or play the other game, where you throw the die until the pattern 5, 5 emerges for the first time. So maybe you throw it once, it's 5, then you throw it again, 4. God damn it, I have to throw it again at least 2 more times, right? Then let's say you throw it and it's 5, then you throw it and it's 5, game terminated. Understand? Which of the 2 games do you prefer, or there is no difference between them? I just want to know if you have a gut feeling about it. That's all. Thank you, Brandon. You don't think there is a difference? right? What about the rest of you guys, right? You understand this game? No, it has to be 5, 6. It cannot be 6 then 5. It has to be the pattern 5, 6 or 5, 5. You understand? And the question is, I want to see just you understand the question. That's my point. Some questions are very, very difficult. If you understood them, then you think they're simple, right? This question is very simple to understand, right? What's happening. Yes, the chance of rolling, let's say, is 1/6. So each number comes out with likelihood 1/6 independently of the previous throw, right? Each time, let's say, you throw the die, you know, the odds are that it would end, that you would get a 5 is 1 out of 6, correct? Right? So you say no difference? Yes? All right, so you want to know what I say? If you play the first game, you will pay on average $36 per game. But if you play the second game, you will pay on average $42 per game. And yesterday I talked with a guy that asked me this question. He was my former student, and he simulated it. Because the question is kind of pretty cool. He simulated it with 100,000 games on the computer, and he got numbers like for the first game, it averaged to be 35.9 something. And for the second game, 42.0 something. That was right. You see? And you see how subtle it is, guys, right? So when you think that something, the thing is, I thought as well, like you, I thought maybe there is no difference, but something was itching at it, right? I thought it's not that simple. So every time you think something in probability, it's very, very confusing, right? And everything else in mathematics, right? So when you think something is obvious or self-evident, that's one point I'm trying to make to you. You might be extremely wrong. So limit laws also require proof. So you become obsessed. You become so terrified that everything that you might attack or touch is completely incorrect. You become obsessed. You prove even things that seem to you are very obvious. Because if you could prove them, then they are true. And if you cannot prove them, then maybe they are not true, or maybe they're not that obvious. Okay. And sometimes you realize that there are extremely paradoxical things that are extremely paradoxical, extremely not like what you imagine them to be. Okay.
So what's the explanation for that then?
I am holding this. The explanation is actually, interestingly enough, I was able to figure it out, but I could not explain exactly why that would be intuitively obvious. You see, I could, with some very subtle things that I could see, I thought maybe that would be the explanation. My brother actually, he also said like you, but actually when I explained to him what's the answer, he actually came up with a good explanation. I like it quite a lot, intuitively. Why
the dice
wait,
were rigged.
which one's?
You want to hear it, huh? Okay, so wait afterwards. Maybe I'll tell you afterwards the intuitive explanation.
Which is the better option?
Huh?
Which is the better option? 5 than 6?
The better option is 5, 6. And if you want to pay less, you understand? The better option is 5, 6.
The dice are
Because
rigged.
that would be on average. You understand how it works? Some people, they go to the lottery, they hope to win. I don't know if they win one time or another, but if they play it all the time, I know for sure that they will be losing $1 essentially, right? That's the law of large numbers. So here, I cannot predict what the game will end up to be, but I can predict it on average. On average, you will pay $36 per game if you play the first game, and you would pay on average $42 per game if you play the second. 5, 5 is worse. You see, I could predict that they are not equal at first, but only because of mathematics, right? I could not see. Understand? I saw through this, right? But my brother, after I explained, he actually came up with an intuitive reason why. I'll tell you maybe afterwards if you want to. It's not going to tell you why it's 42 or 46, but it will tell you why they're different. Okay. You see, I'm trying to entice you guys. It's not too late. You can come and join the probability first, right? And it's very interesting. Okay, anyhow, let's move on with the calculus. And you need calculus, by the way. Oh, how much calculus do you need for probability? Forget about it, right? So here is using graphs to figure out limits. Okay, so here is your task, guys. Can you see it? Can you tell me, please, what is limit as x goes to -2 of f of x plus 5g of x? What is that limit? A. If you, by the way, can figure out what was the message that I sent you, if it's a message at all, you know, extra credit. I don't know where to begin, right? Somebody sent me a ciphered message, or maybe just nonsense to Turchin. You've seen it, perhaps, in my email.
It was the cat.
Huh?
It was a cat.
That typed it, huh?
Yeah.
That's actually a good idea, maybe. But they are specifically, well, maybe, I don't know. It's a very interesting idea. All right, so anyhow, so you understand what you have to do, guys? Sorry for getting distracted. I want to find f and 5gx. Okay, this. So what's the limit as x goes to -2 of f? F is this blue curve, so it looks like it's 1, correct? And gx looks like what? What's the limit of g of x as x goes to -2? It's roughly what? You with me, guys? Yeah, exactly, Zohib. Apologies for pronouncing your name. So at -2, you see we're climbing, you know, we're climbing from both below, from left to right, we're climbing to 2, it seems. So the answer here is f approaches 1 and g approaches 2. So we have 1 plus 5 times 2, which is 11, correct? You're with me, guys? Not confused yet, correct? With me completely, you are able to follow what we're saying? Yeah? Wonderful. So this is 11. Now tell me what is the next limit, if it exists or not. Let's say b. Now we're approaching 1. Yeah, it's okay, no worries. The point is that you understand how to use limit rules, right? That's the idea here. Or that you're not confused by abstract symbols.
Does it matter that it's not specifying if it's approaching it from negative or positive?
Maybe it does. Maybe the limit doesn't exist, right? So you can examine. If you look at this limit and you think it might matter if you approach from left or from the right, you can try each approach separately. Okay. So you see at 1. Well, guys, let me, so I'm not rushing you, think about it a little and then we will talk. Maybe, but okay, let's be careful, guys, right? Rafid. So those are graphs, right? So the blue curve represents y equals f of x. So what does it mean? It means from here that, let's say, f maps 2 to the value 1, it appears, right? 2 is mapped to the value 1. And well, let's say 1 is mapped to the value of -2 by the function f. So the graph can be used to figure out what the function is doing. The function is really transforming numbers back into numbers. Okay, the graph is just a way to visualize what the function is doing. Now g is transforming numbers in this pattern. So for example, at 0, it appears that g is equal to 1, right? A bunch of numbers, I do not know what it equals to, but maybe at 1, g seems to still be equal to 1, hopefully, okay? At -2, g is equal to 0. The functions are, well, they are loosely defined. By the picture, somewhat tells you what the function is doing, but not very precise, right? So this is just an illustration. I do not know what formula is used to process the numbers, right? I only have some sort of representation of it. Make sense, guys? All right. Are we ready, guys? What, are you playing poker with me now? Ready or not? So what's the answer? I don't see any answers really, right? Now, very few things pop out. Random, what's random? What's the answer for limit as x goes to 1 of f of x, g of x? All right, so no limit does not exist. Right, it's pretty nice. Okay, let's see the answer now. Okay, guys, I hope you're not entirely confused. So look at this thing, right? So the limit of g at 1 is roughly 1. So this is always 1, right? But if I approach x from the left, sorry, one from the left, I will get to -2. Do you agree? If I walk on the left, so x goes to 1 from the left, I walk on this curve, I go to -2. That's my altitude. So limit as x goes to 1, here it is, right? Limit as x goes to 1 minus, it's f is -2 and g is 1. But if x goes to 1 plus, f ends up being -1 and g ends up being 1. So the limit does not exist because the right and left hand sides do not agree. I can get either -1 or -2. Do you see that? That's because the f function is ripped up. So if I approach from the right, I get to -1 times 1, and if I move from the left, I get -2 times 1. So the limit cannot exist. Now, next question, hopefully you can figure it out. Now, what happens as x goes to 2 of f divided by g? Here is the graph. I hope more of you will participate. Let's say, so x goes to 2, f divided by g. Here is 2. What happens?
The question was f divided by g.
So yes, divided by g, f divided by g. Let's see. Be careful, guys. It's f divided by g. Notice f is blue, g is the red curve.
A specific value or just in general, f divided by g?
Divided by g, right? And we approach, x approaches 2 from left or right. So be very careful,
Okay.
right? So what, Zohaib, it
Yes.
it is of the form, how do you pronounce your name?
Zohaib.
Zohaib, okay. So Zohaib, 1/0 is the form, but it's not, 1/0 is undefined, right? What's happening, right? So you have to say more precise. And
Okay.
and Nassim, I think you emailed me, and the rest of you, we are roughly in 2.2, 2.3, okay? We are not very far at all.
Professor,
In the book, you know, I'm saying the book is, I think it's 2.2, 2.3, but it's where you can just look into the index of the chapter, right? Cool. And okay, we'll get there. So what are your answers? So wait, no, don't doubt yourself. Maybe you're absolutely correct. We are in chapter 2. Well, chapter 2 is calculus. Chapter 1 is, I guess, review of something, right? Right. I will try to be self-contained, but hopefully you have enough of a background, right? Some things that theoretically you learned from before. Okay, so what's the situation, guys? Look, you see, the problem is that g is, if I move from the left, it's 0 plus, and from the right, it's 0 minus. F is just one, it's just 1 here, right? So it's 1 divided by 0 plus or 1 divided by 0 minus. If I divide by 0 plus, I get positive infinity. If I divide by 0 minus, I get negative infinity. Here is this written again, you see? It just happens. I just look at the graph. If I go to 2 from the left, I am above the x-axis. In other words, I get to 0 plus. Y is where I look. See? You see this graph? Where do I see what happens to G? G, here is G. G is the y-axis, right? So x goes to 2 minus, then G moves actually on the y-axis down. You see? Just project the red curve onto the y-axis. You see it's moving down. So I'm going towards 0 plus. So from the left, it's 1 over 0 plus. 1 over 0 plus is positive infinity. You understand why? 1 over 0 plus means 1 over a million. 1 over a trillion. So it's like I take 1 over 1 of some tiny number. Good? No, 1 over a tiny number to be precise. Right? So that's huge. So the answer is positive infinity from the left and minus infinity from the right. You get it? And this is not a number. This means just that the quantities explode, get larger and larger and larger. And here they fall, they plummet to all the way down below. So the limit does not exist. So here is how the limit laws can be quickly used to construct, to understand what are the limits for many functions. So obviously limit as x goes to a of c is equal to c because c does not depend on what x is. What is the c? This is just a constant. So limit as x goes to 7 of 12. 12 doesn't care what x is doing. 12 is unaffected, okay? So the limit is clearly just that number. Are you with me, guys? This explanation, you are clear on it? Okay, cool. Everybody clear on it, guys? So type quickly yes or something or y, so if you don't want to type something long. Wonderful, okay? So it's just some people are confused by that. But you see, this is just abstraction, right? You're just talking about any possible number combination. So x goes to one number, and this is possibly a different number from a. And this number is not going to be affected by what x is doing. And the other very trivial idea here is if x is becoming a, what's the limit? Obviously, it's a, because if x is becoming a, now you're asking what is x becoming? You understand? You're repeating the question. The answer is trivial. And so those are two limits that I know without any extra effort. I know this one and I know that one. So then I can easily figure out using the multiplication law, what is the limit as x goes to a of x squared. You see, because I can write it as x times x, and that's a product law, right? So this is going to go to a, and this is going to go to a. So by the limit of the products law, I get a squared. You with me? So here I now know that for x squared at least, taking the limit is the same, it gives you the same result as plugging in the value. You understand? It's not the same process, but the result ends up being the same. It's like, you see, think about this, right? It's not the same, right? You might walk home through a very dangerous neighborhood, or you might walk home through a very nice neighborhood, but you end up, let's say, if you end up in your house, the result is the same. Okay, so that's what I'm saying over here. So the process is very, very different, but the result is that you end up home. Good? Oh, guys, I was worried. James, you're here. I thought you disappeared. I started thinking what happened to James. Okay, so, good, good. Glad you're here. It seems I had more people, so they are dropping, right? So what we have here is x approaching a of x cubed. Now that I know the answer for x squared, I know that I can break x cubed into x squared and x. Now it's a product of two functions whose limits I already know. This is going to be a squared, this is going to be a, so I get a cubed. You see, I use recursively the product laws, and I get a cubed here, you see? Good? And in general, if n is any positive integer, limit as x goes to a of x to the n can be, you can recursively obtain it, you know, by using the law for multiplication, and you will see that it's a to the n. Good? So that means that for x to the n, there is no reason to, you know, there is no reason to bother with anything. You just plug in the value. Okay? To take this limit, just plug in the value. Now, figure out limit a, please. You see, and tell me step by step, right? So you don't have to write it here, but we'll do at least one such tedious exercise. Justify what this limit is step by step, quoting the limit laws. Which laws are you using to justify each step? We're doing, let's say, A for now, but if you can do B, that's wonderful, right? And once you do it slowly, just to see that you understand how the limit laws are used to carry out each steps. Yes, Pavel, you are absolutely right. But well, I don't want you to bother writing, of course, the step-by-step solution just in the notes. But you know, hopefully you see each of them, right? All right, so let's do it together, guys, right? You see, first thing is you see a bunch of terms subtracted or added. So we use laws for addition and subtraction. We can break it into chunks, right? So first chunk, then the next chunk, they're called summands or whatever it is, right? So we break them apart and we have laws 2 and 1, subtraction and addition. Really, I would have combined subtraction and addition into one, but yeah. Then you have the constant, right? Here, I can factor out 2. So any constant times a function, I can factor out the 2. So here I factor out the 2, here I factor the 3. So I have this situation. And now each of those limits, I already know how to evaluate. So this is recursively by using, well, this is using the product law. And this is using just tautology. As x goes to 5, x is obviously going to 5. So then I have 39 as my answer. You see, I justified by each step by quoting the limit law that I used here. And I can do the same thing for b, right? If x goes to -2 of this expression, the first law I will use is, of course, the quotient law. So you see, I use the law 5, quotient law. And then in the numerator and denominator, I break using the remaining laws. And the answer is -1/11, okay? No problem there. Again, I cannot emphasize enough. This is coincidental. Simple function, limit does not yield new information. I mean, in other words, does not yield new results. Of course, those PDFs, guys, are posted on my website. You can read those PDFs. You can have those notes at any time. And the video is on YouTube. Good?
Hey,
You can
Professor.
afterwards look, you go to my website, iatkin.com, correct? And yeah, here it is, somebody posted it. Good. You know how to find everything, right? So if not, just send me a message. It's iatkin.com, where you go and everything from there, you just jump around. You will find everything you need, I think. Okay, good. So here, let's start examining functions like we do in zoology. We examine animals, okay? So I often find that people, they don't have an adequately good sense of the objects they deal with, and that can be confusing. If you don't understand it, if you don't have experience with it, it's very foreign to you, okay? So you see, if I ask you to describe a spider, you will give me interesting description. You will say, oh, this is an animal that has 8 legs, or who knows, maybe 8 eyes as well. I don't know how many eyes spiders have. And you're definitely more familiar with zebras, right? If I ask you to describe a zebra, you would say, oh, it looks a little like a horse, and it has white and black stripes. You would say something, right? That would be descriptive.
Yeah.
Good. But with functions, you tend to know them worse than you know spiders. You tend to know them as good as maybe some alien creature or something that you've never encountered before. So let's see if it can be improved. So first, we want to know what are the simplest functions that you can possibly create. Simplest functions. Again, remember what a function is in our context. A function will, in our context, will take numbers, process those numbers, digest them, and spit out a new product, right? It would spit out another number. So that's the business of f of x. You understand? F of x, it means, well, should I show you an image of f of x, right? So here, right? If you look at this expression, if this were a function, this just tells you the digestive process. It means the input is squared multiplied by 2, then you take input, subtract 3 times it, plus 4, okay? So this tells you the digestive process. How is this number that you put into the function transformed to the new number? So what are the simplest operations that you have ever encountered in your life? In elementary school, I imagine they were first addition and multiplication. Addition, subtraction, and multiplication, okay? And then you start learning division, and eventually you learn about roots, and then you expand to other things. The operations become less and less familiar, correct? But in school, the first thing you learn to do is add. So you would imagine that the easiest operations, by the way, addition and subtraction, I can view them once I know negative numbers. I can view subtraction as adding a negative number, okay? Just so that I use fewer vocabulary. So when I say addition, I mean also subtraction, because if I want 5 minus 2, I say add minus 2 to 5. Good? That's convenient, okay? So really, simplest operations will only involve addition and multiplication. Do you agree? Hopefully you do. So functions are operations that can be described only using addition and multiplication. Do you understand? Polynomials are functions that can be described with the process of addition and multiplication. And here is an example, right? So look at it. You see this expression? I only see multiplication and addition, right? The minus 7 means I add minus 7, right? So I only see addition and multiplication, correct? So this will be a polynomial because I don't see any other operation. Now, any polynomial, look at it. I can take this and I realize, try to do it if you don't see right away that's true. Try to do it with some examples, right? I can arrange, make it pretty. I can arrange the operation based on how many times the input x was multiplied by itself, okay? So you see, I expand this and then I group like terms. So here, all the constant terms, I never use x. X, by the way, is the input. You see, what is this? You see, some people see an x. That's not what you should be seeing. This is a placeholder. This means food goes in, that food is a number. And then what happens to this number? This is the digestive process. 5 plus 2 times the number minus 7 times the number, etc., right? That's the digestive process. So I can group all the constant terms together, and then I can group all the terms that involve multiplication by the input once, and then all the operations that involve multiplication by the input twice. That's the x to the 0, x to the 1, x squared, and so on. And I can arrange it in this form, you see? I can arrange it neatly into how many times I used x. Are you with me? So this is not just nitpicking, guys. It's pretty significant. If you understand what's a polynomial, it's pretty significant, not just mathematically, but also in computer science, because you might say the only operation that computers can do is add, and you can simulate multiplication through that. You understand? So this is just a sort of vocabulary that you need to understand. So a polynomial, once you arrange it appropriately, is something that would have this functional form. It means a constant times the input, a constant times the input squared, all the way to some constant times the input to the power n. That's a polynomial. We will ask interesting questions later on, right? I will ask you if something is or is not a polynomial, and the answer will be less obvious than you think. Okay, and those numbers in our context are real numbers. We're not going to explain what real numbers are, but let's briefly recall notation. This symbol means belongs to a set, okay? So when I say this, I mean all those are elements of the real number line. And then we have this basic notation. Natural numbers, n, I write it like this. It's usually a thicker leg for the n. It's whole numbers starting from 1 and going to 2, 3, 4, and onwards. Z, those are integers. 0, plus minus 1, plus minus 2, plus minus 3, etc. Now you might wonder why Z is for integers. The German word for integer or for a number is Zahl. So it's from German. Okay, so Zahl means in German number. So that's what the Z stands for. Q stands for rational numbers, fractions. So integer divided by another integer as long as denominator isn't 0. And what is R? That's pretty complicated, right? So usually when you go to advanced presentation of this topic, you begin by understanding what is R, because there are going to be different theorems, different things, very intricate, very interesting, strange things are true about R that are not true about some other structures. So you need to understand this calculus on this structure, you understand? So complex analysis that involves imaginary numbers works very differently from real analysis, okay? I might give you some brief highlights into it, but that's a different subject. So most likely every single number that you encountered, that you ever used, was a real number, okay? That's what I would say. And the membership is as follows. So every positive, every natural number is an integer, every integer is a rational number, every rational number is a real number, okay? So there are bigger and bigger categories here. So here is our next task, guys. You see, you understood what's a polynomial? Let's see that. Tell me if A is a polynomial. And not only, don't forget about this, right? That you might kind of ignore everything I say and think, oh, I remember something from school, polynomial, right? What is a polynomial? What am I asking? I'm asking, is this function a polynomial? I want to know not only if the answer is yes or no, but what am I asking? Guys, I'm not too loud, by the way. I'm speaking excitedly, and maybe I scream into your ears. You tell me if I bother you. Okay, so I wait for your answers, guys. Tell me if we are dealing with a polynomial or not. No variable, no. So a lot of people say no. Let's see. No, okay. So everybody here said no. Let's see. Do others join together? Do you join the herd, or do you say something else? All right. So you said no, guys. But would anybody volunteer and tell me what is it that they said no to? What did I ask? I asked, is it a polynomial? What did I ask really? In very simple terms. I want to hear your voices, guys. Come on. So Carolina, there were no limits spoken about. There were no limits spoken of. I'm sorry. So the question is first, what am I asking? Could you phrase my question in a very simple form? Let me try this. It's much simpler. Am I a zebra? Come on, tell me if I'm a zebra.
Do
One
you
person says yes. If yes, then why am I a zebra?
do you identify as one?
Ah, come on. You are in this, what is it, postmodernism, whatever it is, right? It's an annoying thing, right?
If you're a zebra, then you would have had stripes and you would have been a horse.
Exactly, right? So I don't have stripes, right? So if that's the property of being a zebra, I need to have stripes. Even if I identify or not, right, I need stripes. So similarly here, if I'm asking something is or isn't a polynomial, what am I asking?
Aren't you asking for a polynomial, right? So aren't you asking so basically with polynomials, right, you can have several different types, of answers because of x, right? Because in a polynomial you have like what, x squared plus x and then a random number, right? So is it more like that?
You have to see, James, right? So what you said, if you think about it, it's big, right? So different answers, several different answers, a bunch of x. No, right? What you should think about is this, guys. Let me repeat, right? People miss it all the time. You see, and in the books or in high school, they kind of give you some, I don't know, explanation that's not really meaningful in my opinion, right? When I say something is a polynomial, it's like saying something that can be described using only two operations, or let's say simple analogy with a language, right? What can I say with only two words? Let's say, I hungry, for example, right? I have I and hungry. How many things can I say with those two words? How much meaning can I communicate with two words? Okay, so a polynomial is a very similar thing, except not words. How many things can I communicate using the operations of multiplication and addition? You understand, guys? So anything, what is the polynomial? It's, you looked up. I ask you again, right? So can I communicate what happens here, right? So the function eats an input and always gives you out 5, right? It processes any input into 5. So if you feed it a 7, it will give you a 5. It will feed you a 1, it will give you a 5. By the way, I'm not sure if you know the Russian grading system. 5 is the best Russian grade you can possibly get. You can never be above than 5. Actually, one girl, right, pretty cute one, right? She says, you are at most a 5. And I said, yes. I was so happy because Russian cannot be more than 5, okay? But Germans do it in reverse. Germans, they, for them, 5 is the worst grade, 1 is the best grade, okay? They have the
In
same
one of my
system in reverse.
schools, I used to have like at one class I got like it goes. That was like it when I was at school, like at one school, like where 1 is the highest and 4 is the lowest. So, and on the other extreme, there are some classes where 4 is the best and 1's the lowest. So it depends.
Well, some people don't give more, but Russian, I mean, traditional, it's supposed to be 5 is the best grade. Well, great, huh? Some people studied in Russia, right? Your grades would be the best in Germany. You can go to Germany with your grades and think, wow, right? We definitely take you anywhere you like. So, good, guys? So,
Is it like any equation that has a variable and or coefficient, something like that?
So simply, right? Can I express the digestion of any input into 5 using only addition and multiplication? Can I do that or not? If I cannot do that, then it's not a polynomial. If I can do that, it is a polynomial. Do you get it? This is, you have to think about it, guys, right? And I will ask you strange questions. I will ask you, is, let's say, e to the x or sine a polynomial? So I want you to understand straight ahead, what is a polynomial? This is just a form, right? A polynomial is something that has this form, but why should it have this form? That's just a neat rearrangement. Anything that can be expressed only with addition and multiplication can be placed into this form. I try to give you an example, okay? So can I do it with 5? Let me help you. Of course I can do it with 5. Here, 5 plus 0 times x plus 0 times x squared, let's say, right? So I can definitely communicate 5 using only addition and multiplication. In fact, if I don't need to use any operation, you might say I can communicate. I have enough, right? What can you communicate with 2 words, guys? I am hungry. You can also communicate silence. You don't have to speak. So, right? So that's similar. You don't need to use operation. You are allowed to use them, but you don't have to. Make sense? So if I just use addition, that's a polynomial. If I can use at most addition and multiplication, I can use nothing or a part of it, but no more. You understand? Are you with me? You look confused, which is too bad.
Then what would not be a polynomial?
We will look at it in a moment. Very confused, Hadi? Well, that's great. Confusion is a state of consciousness. That means you realize you don't understand something.
Wait, sorry. So you said if you can use addition with it, then it's a polynomial? Is that
If so again, guys, right? So if the operation, so you understand what is this x, first of all, right? You put an input and the input is processed. So it's a number, there is no x, right? I put 7 into here, it will be processed into a 5. I put -10, it processes, the function processes this -10 into a 5. I put 0, it will be 5. I put pi, it will be 5. That's what this function is doing. Everybody is with me? And can this operation, can this digestion process be described using only addition and multiplication? That's what we are asking. And naturally, yes, it can be, right? First of all, one way to do that is not to use anything. You don't need to, it's already good. The other way is to do this, okay? Now, is this a polynomial? B, is this a polynomial? Yes. And you understand why it's a polynomial. Not because you might recognize it from before. It's really a polynomial because what do I do here? I use here 7 times multiplication of the input by itself. Then I multiply it by -3. Here I use twice the multiplication of x by itself, then by 5. And then I have this combination, which is addition. You understand? Addition and subtraction, we can just call addition. Good? You understand that B is a polynomial because I only used operations addition and multiplication. Good? With me, guys? Say you understand. No longer confused, I hope. Good. No, not confused. That's important, guys. You see, because if your understanding of those things is very vague, I cannot show you some very, very remarkable results. They're remarkable. Okay. So, what about C? Is this a polynomial? We have x to the -2 plus 7x cubed plus 3. Is this a polynomial? So interesting. A bunch of people say right away yes. By the way, could you type what am I asking? Right? Very simply, if I say is a polynomial, I'm asking you what? Okay, Raquel says we're gonna have division. Interesting, interesting. So some people say still yes. They were not confused now, but so look at it. X to the -2. What is that? It's 1 over x squared, correct? It's 1 over x squared. So we use division here. We use addition, multiplication, but we also use division. So we use an extra operation. You understand? Extra operation. We are only allowed addition and multiplication if we want it to be a polynomial. But here I have division. Now, just because I have division, maybe if I am clever. All right, Carolina, have a good one. So guys, are you there? So I use division here, but maybe because I'm not clever enough, maybe I can express it more efficiently and not need to use division. How do you know if that's impossible? You understand? Just because something is expressed one way, maybe that is not good enough. I will actually explain to you one way that for this question, I'll let you know how I know it's impossible, okay? And then you will figure out for the remaining ones. Look at it. If I could express it as a polynomial, if I could find another formula that does the same thing, multiplication and addition works with every real number, correct? But here, if I put in 0, it's undefined. You understand? Multiplication and addition works with every single number. But throw in a 0 here, it doesn't work. So there is a difference, right? If it could be expressed using only addition and multiplication, there will not be problem plugging in any number, but I have problem plugging in 0. So it cannot possibly be polynomial. Make sense? You look, guys, you know, you look glazing, right? Your eyes are glazing. That is the eyes that I can see. Are you with me? Do you have a pulse? Arisa, are you alive? No? Where, what bothers you, Arisa? What tortures you? I mean,
I was just saying that I'm only half alive, but it's fine.
Yes, well, trust me. Well, I am already, what, 1/16 for life. So, you know, at least you're better. So again, guys, you don't see if you find this to be kind of tedious right now, that's because you don't realize what is this thing that we're talking about. I will try to, maybe in a few lectures we will see a bit more about it, right? It's pretty incredible. If you wonder how your calculators perform anything, let's say you type in the square root of 5 and you get the answers, right? How is your calculator able to do that? Computers are only able to add and multiply, essentially to add. Multiplication can be simulated with addition, understand? So when you ask whether something is a polynomial or not, you are asking, can I make a machine do it, for example? That's one thing of the things that you're asking. Can I make a machine understand or process it, or explain to a machine that it can actually do it? So everything that you see around yourself, right, the entire theory of computation, right, is based on such ideas. So, okay, this is not a polynomial. Let's go to D. Tell me if this is a polynomial. Think about it. Is D a polynomial or not a polynomial? So 2 people say yes, polynomial. You understand what you're saying, guys? Again, can it be realized, this operation, using only addition and multiplication? Clearly, you have division here, right? So I have addition, multiplication, and division, which means, can I get rid of division? Can I express this function without ever using division? And if the answer is yes, then it's a polynomial. If the answer is no, then it's not a polynomial. Good? So a lot of you say yes. And let's see the solution. So yeah, so the expression, look at it. Here in factored form, it's x squared times x plus 1 over x plus 1. So you can cancel out x plus 1 and you say it's equal to x squared. But the problem is it equals x squared only when x is not equal to minus 1. Because when you cancel that out, you assume you are not dividing by 0, which means x cannot be minus 1. You follow? X is not minus 1. So this is a very trivial, you know, so in complex analysis, you would have just simply said it's a polynomial because it's a trivial exception. But to be precise, x is not equal to minus 1. So this function does not digest minus 1. So precisely speaking, it's not a polynomial. It's called a removable singularity. We'll talk about it later. So I would say the answer is still not a polynomial because I cannot process at minus 1. Next, let's look at E. Is this a polynomial? E. We're almost done, guys. Just a little bit longer. So D is not a polynomial, strictly speaking. Okay, the difference is actually trivial in many applications, but it's not a polynomial because when I cancel out x minus 1, I assume x minus 1 isn't 0, which means I assume x is not equal to 1. So E, you're saying, is not. Let's look at E, guys. So now Nassim says that E is a polynomial. You see, guys, again, right? So I'm hoping you stay motivated. If you think this is kind of why it bothers us, if you understand what's a polynomial and what's not, you're one step closer to understanding how calculators carry out calculations. Okay, I can show you. I can teach you quite interesting things. And not only that, I can show you applications. So very important to realize, first of all, the objects we're dealing with. So the answer for E is that it's a polynomial. Why is E a polynomial? Because this time I factor out x squared plus 1, which never equals to 0, correct? X squared plus 1 is never 0. I can cross it out. And I just have that this is the polynomial x squared. So you see, I was able in this case to get rid of the division sign, so it's a polynomial. Even though the original expression used division, I was able to throw it out, go around it, so to speak. So, Alisa, makes sense? Completely, yes? Good. So no longer kind of fried. Good. Well, let's see about it. Good. I hope, guys, it makes all sense to all of you. If not, tell me, okay? Here is the next question. And again, I'm trying to teach you to think about it, right? F, is this a polynomial? X to the 1/2 is the square root. Is this a polynomial? And I want, of course, to know why or why not. Great, Alan. I'm glad you do. Now, Victoria Factor, we definitely have to believe Victoria Factor since she is a factor, right? So everybody, she has a math name. We are asking for F, right? F is 5x to the 1/2 plus 2x cubed. Is this a polynomial? All right, so first I want to see how many of you say no or yes, and then we will try to ask you for reasons. So Malika says no. Brian says we need division. Well, actually, who knows what we need? It's x to the 1/2. How do you perform square roots? Okay, I want to know more, guys. Would anybody tell me, how do you know it's not a polynomial? Well, one reason is you see square roots are definitely not an operation that you easily carry out. Addition, you know, I can give you two numbers, right? You can add them, correct? If I give you two numbers to multiply, you can write a table and essentially you can multiply. Maybe you don't know how to multiply irrational numbers, but definitely if I give you a string of digits, hopefully, right? You will be able to multiply one string of digits by another. You have this multiplication, what do you call it? You know, on paper where you have this multiplication algorithm. You will know how to carry it out. But for square roots, I'm pretty sure most of you would not know without a calculator what to do if I ask you, find the square root of, let's say, 5. Correct? So it's definitely a suspect. We don't really understand how to carry square roots. Besides, what is the square root? It's defined as the unique positive number that when multiplied by itself gives you the input, right? So for example, square root of 25 is 5, because you know that if you take 5 and multiply by itself, you get 25, okay? So it's like really guessing in reverse, okay? So I will tell you that F is not a polynomial, but the question is why? Maybe I just not clever enough to figure out how to write it with only addition and multiplication. How do I know I will not be successful in writing this expression using only addition and multiplication? At least finitely many additions and multiplications. There is an issue of actually using it infinitely many times. It becomes interesting. Okay, with describing the square root with only finitely many additions and multiplications is impossible. How do I know that? Well, you can square root 0. 0 square root is 0. So that's a good attempt, Rachel. But 0 I can. Maybe think about it. Maybe you're on the right track. How do I know the square root is not a polynomial? Yes, it's not a polynomial, but how do I know that? You understand why I know it? It definitely does not look like it's a polynomial form. But maybe I can find another formula that is able to do the same thing. Exactly, because x cannot be negative. You see how I reason, guys? You understand? Suppose that somebody came up with a formula that only involved multiplication and addition. Are you getting me, guys? If somebody came up with a formula that involves only multiplication and addition, then this formula would work for all numbers. But I now see that if I plug a negative number, square root of negative numbers, for us at least, for the real number line is not defined, correct? there is no square root of minus 25 because any negative number multiplied by itself is positive, so I don't get negative numbers this way. Any positive number multiplied by itself is positive, and 0 multiplied by itself is 0. So I cannot take square roots of negative numbers. So this operation cannot be simulated using multiplication and addition alone. Good? You understand me, guys? But yet calculators are able to somehow give you approximations or give you some values, right? That's the question. How? Because you understand, calculators, what they do, they add and multiply. You understand? So that's essentially the question we're asking you. Can you create a machine that will carry out those calculations? And they're kind of interesting things about square roots, right? Some people, I remember giving a lecture, and people were extremely bored. You know, there was a guy and a girl even kissing in this kind of room, right? So I said, you don't care about square roots? Okay, so then you would not mind if I take a brick and drop it on your head. And that's one of my lectures. If you are interested in it, I'll show you one afterwards. Well, so for today, we said enough. I hope. I'm pausing this video. If you want to ask me questions or talk about something, go ahead.